So how about I get started? Two announcements. First, I have posted your fifth homework assignment on Moodle. It's going to be similar in style to the one that you all worked on over this past weekend, except now we're testing hypotheses. I have not yet programmed the submissions into Moodle. And there is something kind of tricky. I'm trying to decide how to ask a question, like, do you test or like, do you reject the hypothesis or not, aside from making it just true, false, which is a little bit too easy. Doesn't give you enough feedback if you just say true, reject the hypothesis, and it says, nah, wrong. Like that might not be useful feedback. So I'm trying to think of how to set up the grading in Moodle so that you get the best experience. Like you're really practicing to get experience, So anyhow, but go ahead, start working on that when you're ready. You have most of the tools for the assignment. Okay, second thing is your next test. I'd like to do that not this upcoming weekend, but the following weekend. Does that sound fine with everyone? Okay. It was originally scheduled in the syllabus to be this upcoming weekend following Halloween, but if anyone objects to moving it a week later, let me know. Otherwise, I do plan to have it next weekend. Okay. And final thing I wrote on here is completely irrelevant for this course, but I learned today that the word estimate means to calculate the value of copper. Or actually as, it was the Roman word for copper, and timate means to value. Okay, and so, fun fact that I learned. Okay, so, so let me do a quick recap of what we did last Friday. So we talked about a couple of new considerations when testing hypotheses. Okay. One is that sometimes we're interested in what are called one-sided tests. Okay. And a one-sided test is more interested in the direction, not the specific value. Okay, so we might be interested in and it most often shows up as an inequality in one direction. So you might be testing a null hypothesis like theta is greater than or equal to a value against the alternative that theta is less than that value. Or it could be just reversed from that. The null hypothesis is that theta is less than or equal to 2.13 against the alternative theta is greater than 2.13. So it's about greater than a value versus less than a value. Which side of the value is it on? Okay, which direction? Okay, so again, sometimes we're interested in these things. The example that I gave when I started talking about hypothesis testing, I talked about Ronald Fisher's question of, do identical twins exist? And he basically said, well, either one of two things is true. There are no identical twins, and in that case, half of twins will be same sex, or more than half of twins will be same sex because we have some identical twins mixed in. So it was really about, is the proportion of twins who are same sex more than a half? So to state it properly, that was a one-sided test. Now, a little note on terminology. Okay. The book uses the phrases left-tailed and right-tailed test. Okay, left tail and right tail test. Okay, it's referring to what shows up in the alternative hypothesis, and left tail means less than. Okay, right tail means greater than. Okay, like if you think about the number line, the numbers in the left tail of the distribution are the numbers that are less than some value. Okay, whereas the numbers in the right tail are greater than some value. Okay, so the names left tail and right tail are confusing to me. The textbook uses them, and again, I'm explaining them in terms of like less than versus greater than. Okay, so one-sided tests. Okay, and there was a simple modification. Is basically use z of alpha instead of z of alpha over 2 when constructing a confidence interval, when calculating a critical value, if using a p-value, do not double. Okay, we're interested in only one tail, so we don't need to double it to account for the possibility of being in either tail. Okay, so next thing that we talked about was the topic of unknown population variance. Okay, so keep in mind that when I write sigma squared, this refers to the population variance. Okay, in contrast to S, which is the sample variance. When I first introduced you all to working with confidence intervals and hypothesis testing, I gave you all the population variance. Okay, one reason is it's simpler to start with that. Okay, but the challenge is typically we don't know the population variance. We're interested in testing a hypothesis, but no one tells us how much variance is truly in the population. I use the example of IQ scores a number of times because there is a case where we know exactly what the population variance is. The people who designed the IQ test intended for it to have a population mean of 100 and a variance of 225. The test was set up that way. So it is a case where we know the population variance. But most of the time, that information is not given to us. Now, we can always calculate the variance in X in our sample. And that is what we almost always do. Okay? So, okay. Keep in mind though, even though the population variance has some specific value, like 225. That doesn't mean that when we collect a sample, we expect that our sample variance is going to be exactly 225 each time. Sometimes we'll get our sample variance a little bit lower. Sometimes our sample will be we'll have a little higher variance. So the sample variance is different from the population variance. Now, in principle, we ought to use the t distribution with the sample variance. Okay. However, it doesn't make much difference in a large sample. So as a practical matter, the real distinction is if we are testing a hypothesis about means in a small sample, and we are using our sample variance, we must use the t distribution. Okay. In a large sample, the z distribution is acceptable. Okay, so this is the practical consideration. So there is actually a good justification for using the z distribution most of the time, even when we don't know the population variance. Okay. Then I moved on to a new topic, testing a hypothesis about less fun hypothesis testing. Okay. So testing a hypothesis about comparing two different samples. And we'll start with testing a hypothesis about whether two sample means are equal. Okay, so kind of the framework here that I'm giving you all, we have group A and group B. And group A, we surveyed 100 people, and we found that the average value of X was 54. Group B, we surveyed 200 people, we found the average value of X was 53. Now, we might want to know, is it possible that these two samples come from populations that have the same mean? Or are the populations actually different? Like, is 53 versus 54 does that represent a real difference in the averages in the population? Or are they basically coming from the same population, and one time we got a slightly higher sample mean than the other time? Okay, now, I want to bring up a couple of considerations. One is we could assume that the means of, I'm sorry, not the means, but the variance in the two samples is the same. Alternatively, or instead, we could not assume that. Okay. And there are different techniques for testing hypotheses in these cases. Okay, I am not going to teach this method where we assume they have equal variance. Okay, turns out that you don't need that assumption, and you know the dumb joke about what the word assume means? Should I explain this? Oh boy. Okay, word assume means to make, okay, someone fill us in, means to make an ass out of you and me. Okay, sorry, it's a dumb joke, but I feel it's appropriate to bring this up when teaching, right? When teaching statistics, there are times when people make assumptions, or when teaching economics, a lot of our models make assumptions. If we assume that a market is perfectly competitive, then discrimination is unprofitable, okay? That's something that when I teach labor economics, I can show that's true, okay? But there's an assumption there, if the market is perfectly competitive. If the market is not perfectly competitive, then the statement doesn't follow, right? If a market is not perfectly competitive, there might be reasons why a firm can remain profitable while discriminating against kind of able workers. Okay, so it's important to address assumptions. And here is an assumption where I feel there's no need to teach a special case when we're willing to make an assumption, and I'll just do the general case instead. Okay, so a second thing is all the considerations about known variance, unknown variance, small sample, large samples still apply. And if we're working with a small sample, we do need to use the t-distribution. Okay, and the formula for calculating degrees of freedom is pretty gnarly, okay? I don't like it. I'm going to teach you all that the degrees of freedom are approximately equal to NA plus NB minus 2. Okay. Which is close to what the formula will always give you. There's just a small adjustment. Okay, so degrees of freedom, total number of observations minus 2. All right, so I just want to put up those considerations as well. But then return to the problem. Okay, so, okay. Okay, we want to compare two samples and test whether the mean could be equal against the alternative that the means could be different. Now, we typically state our hypotheses in the form of some parameter, some parameter equals a value, okay? And what I would say is that the difference in means equals 0 against the alternative that the difference in means is not 0. Okay. So in other words, if we're interested in testing equality, that's logically the same as testing 0 difference. Okay, but the second way, like 0 difference, fits with the format that we use for testing hypotheses. Okay, so the one thing that is new is that the variance in the difference in sample means is given by a different formula. It's the variance in group A over number of observations in group A plus the variance in B over the number of observations in group B. Okay? When we're testing a hypothesis about just X bar. It was variance over number of observations. So testing hypothesis about the difference in X bars is like variance in one group over number of observations in the group plus variance in the second group over number of observations in the second group. So it's just the same term for both groups. Now, keep in mind, what we use in the formula is actually the square root of the variance in X bar. So it's the square root of variance in group A over number in group A plus variance in group B over number in group B, and reminder, the square root of A squared plus B squared is not square root of A squared plus square root of B squared. Are you all clear on that? Right? In other words, when you evaluate what goes in, like when you evaluate the standard deviation in the difference in X bars, evaluate everything under the radical together, then take the square root. Don't split it up into two different square roots. Okay, that doesn't work. Okay, so, all right, now we go to our problem. We want to construct a confidence interval, theta hat plus or minus z of alpha over 2, since it's a two-sided test, times the square root of the variance in the estimator. Okay, specifically we're talking about the difference in means. So it's the difference in X bar plus or minus z of alpha over 2 times the square root of, and we'll use our sample variance in A over the number in group A plus sample variance in group B over the number in group B. And then we start plugging values into this. So the difference in means, 53 minus 54 plus or minus, and then z of 0.005 times the square root of, variance in the first group was 4. Number of observations in the first group was 100. Second group had variance of 8, and the number of observations was 200. Is that correct? I believe that's correct. Okay, so this is -1 plus or minus, and then we look up what the z value is for 99% confidence. I believe the answer is 2.58. Okay, something that we use often. Then we have, let's see, this is going to be, let me just double check. Were my numbers? Yeah. Okay, so 16 or 125 over 125. Okay, 2/25 times the square root of 2 over 25. Okay. Okay. -1 plus or minus 2.58 times, and then this number is 0.2828. So, -1 plus or minus 0.7297. And then we check, is the hypothesized value a difference of 0 inside that confidence interval? Is it? Confidence interval goes from -1.7297 to -0.2703, right? Is 0 inside that? No. Okay, so we reject the null hypothesis that the difference in means could equal 0, okay? In other words, like, based on statistics, it looks like these two samples came from populations that had different means. It looks like Group A actually has a different average than Group B. All right, do you follow? Okay. Now, okay, the last type of example that I want to bring up is testing a hypothesis about a difference in proportions. Okay, so imagine that we conduct a survey and we interview two different groups. Okay, Group A has 100 people, Group B has 200 people. We estimate that 60% in Group A, I don't know, like the candidate. So maybe we're comparing voter preferences of people with a high school degree to people with a university degree. And we see that among our high school graduates, 60% like the candidate. Among the university graduates, 65% like the candidate. Okay, that's in our samples. Do we believe that represents a real difference in the populations, or is this just like sampling difference? Could it be the case that they both have kind of the same underlying preference for the candidate, and we expect some variation from one sample to another? Is this within the variation that we typically get from one sample to another? Right? That's the question that we're asking. Okay, so we want to test this hypothesis. We have some confidence level. Okay, here we're testing the hypothesis that the proportions could be equal against the alternative that they could be different. Or if we want to state that in terms of parameter, null hypothesis is that some parameter equals a specific value. The null hypothesis is that the difference between the p's is 0, and the alternative is that the difference between the p's is not 0. Okay. Everything remains the same except for the formula for the variance in the difference in proportions. Okay. This is PA times 1 minus PA over NA plus PB times 1 minus PB over NB. Okay. So So it is kind of like the formula for the variance in p hat. I should say variance in p hat. It is like the formula for the variance in p hat, except it shows up twice. Once for group A, another time for group B. Okay, so the confidence interval, again, it's going to be the estimated parameter plus or minus z of alpha over 2. When we're testing a hypothesis about proportions, z distribution is the way to go. There is no better distribution to use. Times the square root of the variance in the estimator. Okay, so the estimator is the difference in proportions plus or minus, and then we look up, or well, we'll need to look up z of what confidence level? 95% confidence. Okay, z of 0.0025 times, and then we have PA times 1 minus PA over NA plus same thing for group B, P times 1 minus P over N. Okay, at this point it's a matter of plugging in values. Okay, so 0.6 minus 0.65 plus or minus, and we look up the value of z for 95% confidence. That's 1.96 times, and now we get to the messy term. Okay, this will be 0.6 times 1 minus 0.6 over the number of observations in the group, 100, plus then 0.65 times 1 minus 0.65 over number of observations in the second group. Okay. And now it's a lot of like plugging into the calculator. Negative 0.05 plus or minus 1.96 times, and we work out this math. Okay, so this is 0.0024 plus 0.0011 okay, so negative 0.05 plus or minus 1.96 times, and then 0.0595. 1.96 times 0.0595 is, okay, so negative 0.05 plus or minus 0.1166. Okay, and again, check whether the hypothesized value 0 is inside the confidence interval. Is it? You take negative 0.05 and you add 0.11 to it? No, right? Okay, so this goes from like what? Negative 0.1666 to plus 0.1166. 0.066. Wait. Yeah. 6. Okay. And we're testing the hypothesis that difference in proportions is 0. 0 is inside the confidence interval, correct? Yeah. Okay. So do not reject the null hypothesis. Okay. Are we good? All right. So, at this point, I've got one more thing to talk about with hypothesis testing, and it's a completely different topic. So I think I'll save it till Friday. It does not at all fit the standard format that I've been teaching you all along, but it is a very useful technique to know. Again, let me put that off, sorry, not till Friday, till Wednesday, till the next class. I want to talk instead about the way that researchers talk about their findings, and in particular, the concept of significance. Okay. This word, significant, shows up a lot when researchers discuss their findings. Significance means something about statistical confidence. Okay, and I want to make it clear, I want to explain this term because of what it means, and it's very important. When a researcher says that they find that something is significant, they are announcing that they are statistically confident in a finding. Okay, and that is important to researchers. And that's why that's like them trying to convince you that something is true. But the word does not mean important, okay? So it does not mean important, large, substantial, most importantly, it does not mean that it has practical implications. What do I mean by practical? In this sense, I mean, like, would you take action on it? Like, does it change the way that you do things? And statistical significance is a way of determining whether something is true, yes or no, but it doesn't tell us whether it's important enough to do something about it. Okay? And sometimes when people try to reinforce this lesson, they'll talk about two distinct ideas. One is statistical significance, and the other is practical significance. Okay, statistical significance, as I said, invokes the idea of statistical confidence in a finding. But practical significance is kind of, it's worth doing something about it. Okay? And that's the distinction, okay? Those two ideas should not be confused. Okay, so let me say again, researchers are obsessed. Or let me say, this is an obsession for researchers. And almost every time a researcher announces some discovery or some finding, what they're stating to you is that they have found that it is statistically significant. Okay, and by the way, like one of the applications of testing proportions might be looking at a control group and a treatment group in a medical trial. Okay, so like I gave my example earlier where the proportion in group A was 60%, proportion in group B was 65%. I mean, imagine we were doing some medical test and we had a bunch of patients. We gave some of them a treatment and some of them a placebo or control. Okay, and the treatment group 65% recovered. The control group 60% of people recovered from it. A researcher would want to know, is that like, or a researcher would want to know, is that an actual difference between the groups, or is it possibly just like everyone's recovering at the same rate? You just happen to get a few more people who recovered in the control group than in the treatment group, has nothing to do with the drug actually changed something. Does that example make sense? Right? Okay, and the researcher wants to test the hypothesis. If a researcher says, we found a significant difference between the control group and the treatment group, that means that they have rejected the null hypothesis of zero effect. Okay, and usually, unless they say otherwise, usually with 95% confidence. Okay, but what but the counter argument is, well, fine. So you found a difference. Does that mean it's worth? Well, does that mean it's worth actually administering the drug to people? And for that, you have to like bring in some values, right? You have to think about, well, what's the cost of treating the disease versus not treating the disease? What are the side effects, right? Like, right? And like, is that 5%, or if it were a 5% gap between the control and treatment group, is that enough to justify the cost of the drug and the side effects of the drugs? It depends on how large the benefit from treatment is, right? There are a bunch of values that go into deciding whether you should administer the drug, whether it's a good idea to administer the drug. I say it's a value judgment. That doesn't necessarily mean like abstract subjective values. You could even quantify the values in many cases. Like, well, there's the benefit of living longer. There's the cost of the drug. There's the cost of the side effects. Okay, so you can put in like those types of very objective values and decide whether something has practical significance. Okay, but one thing I'd like to drive home is that something could have statistical significance, but still perhaps not have practical significance. So imagine we collect data on the annual earnings of men and women, and we test the hypothesis that, they're equal. Okay. And, the researcher might report that the researcher found a significant difference. Okay. In the earnings of men and women. Let me again remind you all, when the statistician says that, the statistician means that the statistician is statistically confident there exists a difference. Okay? But the word significant doesn't mean, like a common person would hear this phrase, there's a significant difference in the earnings of men and women, and think, oh, a substantial difference, a large difference. And that is not what the word means in a statistic, like when we're talking about data analysis. It's not saying that it's large. Okay, how large does the gap need to be in order for you to care about it? That's a different matter, right? If I were to tell you, we collected the data and we estimate that women earn $10,000 a year less than men for doing exactly the same job, does that bother you? You think we should enact some legislation to correct this $10,000 earnings difference? I mean, again, it's a value judgment. And maybe, like, you could impose your subjective values on that and be like, wow, 10,000, yeah, that does bother me. I don't sleep easy at night knowing there's so much inequality in the world. Okay. What if it were a $1,000 difference? That women earn $1,000 less a year for doing the same job as men. Does it still bother you? Should we still take action on it? And I'm going to continue saying, like, it's a value judgment, right? And maybe it depends on how much you value equality. My guess is you'll draw the line somewhere, right? If I told you that women earn $10 a year less than men for doing the same job, is it worth doing something about that, enacting legislation to correct the problem? Okay, there's probably some point where the difference can get small enough that you say, no, it's not worth the hassle. Okay, even if the researcher says that it is a statistically significant difference. Okay, so that again means there exists. Okay, that, like, the phrase significant difference means confident that there exists some difference. Okay, but practical significance is about, practical significance is about whether we should take action. And this usually does depend on the magnitude of the difference. The magnitude, how large it is. And as I said, statistical significance, does not address, like, is the magnitude big enough to care about? Okay, so this is one example of, like, the two terms don't necessarily coincide. Okay, I would give another example, okay, of a distinction between what might be practically significant and statistically significant. Okay, imagine two weight loss drugs. Okay. Drug A, 95% of patients taking drug A lose, let me say, 4 plus or minus 1 pound taking drug A. Drug B, 95% of patients lose, let me say, 25 plus or minus 30 pounds. Very different drugs in terms of both the average weight loss and the spread. But now if you think about these two drugs, and you're trying to, you're the doctor, and you're trying to pick which drug is more appropriate for some flubby-wubby patient like me, right? I need to lose some weight. Which of these drugs seems the better choice for me? Drug A or drug B? If I want to lose a substantial amount of weight, drug B? Yeah? Okay. I mean, it's really a difference between drug A is almost guaranteed to lose a few pounds. Sorry, let me say that again. Drug A is guaranteed to lose a few pounds, and that's it. Drug B, there's a wide spread, but people tend to lose a lot of weight on it. Okay, so let me say intuition says that drug B is the better option. Okay, right? You know, it depends. It's a value judgment. What?
Gain 5 pounds.
Well, you could gain 5 pounds. Exactly. Now, I mean, here's something to realize, though. In a statistical sense, drug B, we would say, does not have a significant effect on weight. Okay? Drug B does not have a significant effect on weight. Like the 95% confidence interval for what people lose contains 0, right? And it even goes into like you could lose negative weight. Some people gain weight on drug B. Okay, but some people lose a lot of weight, right? As many people gain 5 pounds as lose 55. Okay, so yes, you're absolutely correct. Some people lose nothing. Some people even gain a little weight with drug B. And so the mentality of like thinking about does it have a significant effect would lead you to choose drug A over drug B, right? Drug A, it's proven to cause weight loss in over 95% of patients. Drug B, does not cause weight loss in 95% of patients. An interesting thing is that the Food and Drug Administration, the FDA, and all of its equivalent agencies around the world are obsessed with statistical significance. Drug B would not get approved in the US. Like in this scenario that I'm putting up, like the FDA would be like, that's an unproven effect, okay? Whereas drug A, yes, that's proven to have an effect. Okay, so, but, okay, it does not have, so drug B is a better option for losing weight. And if you think about, like, what would you do in this case? The answer might be, don't go with the statistically proven effect, but instead recognize that there's an uncertain or a highly variable drug that might have a larger impact. And that might be the better option. Okay, so by the way, I am not seriously telling you all to ditch medical advice and go into unproven remedies. I am, however, critiquing the mentality of the FDA because it is very interested in determining really two things about any drug before it approves it. One, does it have a statistically significant impact on the disease? And two, is there a statistically significant danger of side effects? Okay, but it's very much about just like proving whether things are true statistically. If you were to ask your doctor about some of the drugs that get prescribed, your doctor would say that there are many of them that, yes, they have a proven effect, but it's fairly small. It might be that, like, and this is real, like antidepressants, SSRI class antidepressants, are effective for about 1 person in 10. Okay, but it is statistically proven that the treatment group has better results than the control group, even though it's just like 1 person in 10 who gets the benefit. So, statistically significant, some people, however, might argue that it does not have practical significance. That the size of the effect is so small that it might not justify the side effects. Now, another term, I'll throw this out. Doctors will use the term medically significant. To mean the same thing as practical or practically significant. Okay, so it's a term that they use and they understand it best that way. If you talk to someone in statistics or in social sciences, we will typically say practical significance. Okay, and to the credit of many doctors, they understand this issue. And they understand that some drugs have a statistically proven effect, but the magnitude of the effect is so small that it doesn't justify giving the drug to many people. Okay, let me give another example of something that, like, this is in part my opinion, of something that is not statistically significant, but practically significant. Okay, that's climate change. Okay, I'm a data person. I like try to be as informed as possible and read what scientists have to say about things. Okay, and let's suppose that the scientific community is about 90% confident that people cause climate change. Okay. And that's a conservative estimate. But okay. But let me point out, this is below the 95% threshold for being called significant. Okay. Right. Again, 95% is the usual threshold that scientists use. Okay. So let's suppose that the scientific community believes there's about 90% chance that humans are causing climate change, 10% chance that it's some natural phenomenon. Okay. Now, the standard scientific reaction would be, if we're less than 95% confident, it's not proven. Okay, it's not statistically significant. But, okay, but does it have practical significance? And I would argue that the answer is probably yes, even before we are statistically confident. Okay, because that's a value judgment. There's nothing really magic about the 95% threshold. It's often treated that way, as like a dividing line between things that are true and things that are untrue. Okay, but it's really a matter of things that we are very confident about versus things that we are not so confident about. And does it have practical significance? Would I advocate doing something about it? Okay, because abating climate change is going to be costly, or is costly, right? I mean, probably the best solution to reduce carbon emissions is raise taxes on gasoline and other carbon emitting fuels, okay? That's going to be costly to people. However, like, the consequences of ignoring climate change are much larger, right? I mean, we saw Hurricane Helene was most definitely caused by warm water over the Gulf of Mexico. We don't know that humans caused that warm water, but it was caused by temperatures, and Hurricane Helene did, I believe, over $50 billion of damage to North Carolina. Is it worth intervening and cutting back on carbon emissions, even if, like, there's a 10% chance that strategy is wrong, 90% chance the strategy is right, and it, well, sorry, let me say, 10% chance cutting back carbon emissions is costly and does nothing. versus a 90% chance that cutting back carbon emissions is costly, but it has a large benefit to society. Okay? And I would argue that that value judgment, right? And again, like talking about economic values, like that's what's easiest for me to wrap my head around. $50 billion of hurricane damage is a number I can comprehend. Or, $10 billion of crop damage. Like I can very easily, objectively say those are costs and benefits. Okay. Already I think the balance is in favor of abating carbon emissions or doing something about global warming even before the evidence is completely certain. Okay? So again, I'm doing some opinionating here, but I'm also telling you all my thought process. You don't have to agree with me, and I'm not necessarily trying to teach you all, climate change is bad, okay, or vote one way or another. That's not what I'm trying to do. I'm just trying to explain my reasoning to you all and why I see that, in this case, 90% chance it's successful versus 10% chance it's a waste is already an argument in favor of doing something, even before we are statistically confident about the effect. Okay, so that's it for today.